So let's go back and think a little bit about ordinary calculus as kind of a reminder. One of the first things we do in ordinary calculus is we talk about derivatives and use them to measure rates of change. And one way to think about that is that if we start with an ordinary function, like this function that I've drawn in blue here, we can fix a point and focus our attention in near that point and try and find the closest line to the graph of the function at that point, called the tangent line. That tangent line gives us another function that is a good approximation, at least in a little tiny neighborhood around that point. It tells us basically what the slope is, what the rate of change of the function is right at that exact moment. And so ordinary calculus and derivatives are telling us about linear functions like y equals ax plus b and how we can use those as good approximations to other functions. So we'd like to do that with functions of several variables. If we have a bunch of different inputs and a bunch of different outputs, though, it's not immediately obvious what the right notion of linear function really is. What's what's going to play the same kind of role for us if we have this new situation? And we don't have graphs at our disposal quite as easily anymore. If we've got a function with 5 inputs and 20 outputs, we can't draw the graph of a function, certainly, because we don't have enough dimensions to work with, and we have no way to think about it in quite the same terms. So we have to be a little bit more flexible. And one way to think about this is in terms of change. A linear function is a function where changing the input has a predictable effect on the output, kind of no matter where you are. So with that in mind, here's what a linear function with a bunch of inputs and a bunch of outputs looks like. If we've got m inputs and n outputs, a linear function expresses each of the outputs in terms of adding up something times the first input, something times the second input, da da da, all the way up to something times the last input, and then plus maybe a constant. So that's what happens to the first input, and the second input is the same way. It has some way to multiply and add up all of those inputs and then add some constant. And that's true all the way down to the last coefficient. So that's the simplest way to write these things. And these numbers aij have specific meanings. They tell us if we take the jth input and change it by some amount, then the corresponding output changes by that number aij times the amount we change the input. So we're going to work on making the notation for this a little bit cleaner. Right now it's really long and there's a bunch of redundant information in it. Here's an example function with four outputs and 3 inputs. R, S, and T are the inputs, and X, Y, Z, and W are the outputs. It takes a lot of work to write this. There's a bunch of redundant symbols in here. If you're writing it by hand, it's laborious. If you're trying to type it into a frickin' PowerPoint, it's even more of a pain. And it's nicer to have a cleaner way to express this that A makes it a little bit more readable and B is a little bit easier to use on a day-to-day basis, because the important information here isn't all the plus symbols and equal signs. It's knowing the names of the input and output variables, and it's knowing kind of all these coefficients, all these numerical values. And so what we're going to do is we're going to use matrices to give us a clean way to express all this information.